the following past paper question, the first question is that we need to define what force is. Force is the rate of change of momentum. So it's the rate of change of momentum, or the formula of force is mv minus mu, where mv is the initial momentum, m is the final momentum, mu is the initial momentum, and that mv minus mu gives you the change in momentum divided by the time it takes for the momentum to change. In the next part of the same question, we are being asked to find the SI base unit of force. So I'm going to use the same formula that I just wrote down, and I'm going to derive the SI base unit. So I can rewrite this equation as F and take M as common. So it's V minus U, which is change in velocity. Delta V is change in velocity. This is V minus U divided by time. Now I'm going to figure out the base unit of each of the quantities in this expression. M would be represented by kg. Velocity is meters per second, and we are dividing it by time, which is s. Now if I bring this s to the top in the numerator, this s would also become s minus 1. So if I put the units together, it's going to be kg and into meters into s minus 2, because minus 1 becomes s minus 2. So the SI base unit for force would be kg meters per second square. The next part of the question reads that you have force F between 2 point charges. So this is Coulomb Force. This is the formula for Coulomb Force, where Q1 and Q2 are charges, and 4 pi r square epsilon naught. So it's 1 over r square. So we're given a formula, and he's described everything. Q1 and Q2 are the charges. R is the distance between the charges, and epsilon is a constant that depends on the medium between the charges. And you need to use the above expression to determine the base units for E. So we need to define or figure out what the base units for E are. I'm going to start with F, because for F I've already figured out the base units. So F is kg m s minus 2. So we've already figured that out. 4 pi is a constant, so let's 4 pi is a constant, so it is not going to have any units. I'm going to bring r square over here. So if I bring r square to the top, this r square is the distance. R is the distance. So r is the base unit for r is also meter. So I'm going to rub that off. This would be taken as meter square. So r is meter square, and I'm left with Q1 and Q2. Now Q is basically Q is current into, so it's current into time. So the base unit of Q is going to be amperes. Current is in amperes per second. Time is in seconds, so it's ampere multiplied by second. That's the base unit of Q. So I'm going to make this epsilon the subject of the equation. So E is going to come upwards, and this entire thing is going to go in the denominator. It's going to be m square, meter squared, kg. Then there's another meter, so I'm going to make this meter cubed, s minus 2, and it's charge multiplied by charge. The base unit for charge is ampere per second, so it's going to be ampere squared, second squared. And this over here is going to be this was s minus 2, and I'm going to simplify this. If I bring s to the top, it's going to become plus 2, so it's going to become s to the power 4. If I take m on in the numerator, it's going to become m minus 3, and if I take kg in the numerator, it's going to be kg minus 1. So let's write this down neatly. It's going to be ampere squared, second to the power 4, meter to the power minus 3, and kg to the power minus 1. So I have to write down the base unit now. in the place where they asked me to write it, it's going to be amperes squared, s to the power 4, m power minus 3, and it's going to be kg to the power minus 1. The first part of the question reads that you have to state the principle of conservation of momentum. The principle of conservation of momentum is that the initial momentum or the sum momentum before collision is equal to the total momentum after collision. So that's the principle of conservation of momentum. So total momentum before collision equals total momentum after collision. Moving to the next part of the question, part B. The question states that there is a stationary firework that explodes into 3 different fragments that move in a horizontal plane as illustrated. So you have 3 particles, there is an explosion, 3 particles, one traveling with a mass of 3m, traveling at 7 meters per second, the other one has a mass of 1.5 m and it's traveling at 8 meters per second, and the third one has a mass of 2m and it's traveling at 6 meters per second. So all the masses are provided, and so this is given, and you have to figure out, use the principle of conservation of momentum to determine theta. This angle theta needs to be determined, and we need to figure out the we need to use the principle of conservation of momentum, which was that initial momentum before collision and initial momentum after collision, that's going to be equal. Now in this specific case, the initial momentum is going to be 0. The reason it's going to be 0 is that before collision, in this case collision, the word collision is referring to the explosion that happens. So initially all these particles, they were all joined together, and initially this big particle which had all these masses added up. So you had this one big particle that exploded into 3 separate pieces. One went in this direction, the other went in this direction, and the third is going in this direction. So initially, before the explosion happened, you had this one big particle, and this particle had a mass. The mass of this particle is going to be the sum of all the masses. It's going to be 3m, 1.5m and 2m. So it's going to be 5 plus 1.5, that's 6.5 m. So this initial particle had a mass of 6.5 m, and it had a velocity that was 0 because it was stationary, it wasn't going anywhere. And then it exploded into 3 pieces, and those 3 pieces started traveling with a certain velocity. So your initial momentum is 0 because your initial particle is at rest. Now initial momentum should be equal to final momentum. That is the principle of conservation of momentum. So since the initial momentum is 0, so my initial momentum is 0, so my final momentum would also be equal to 0. So what I'm going to try and do is I'm going to try and calculate this final momentum, what that final momentum would be. So my particles are now traveling at 7 meters per second in one direction, 6 meters per second in the other direction, and 8 meters per second in the third direction. And remember, momentum is mass into velocity. It's a vector quantity. So I'm going to divide my final momentum into vertical components and horizontal components. So my components are in the horizontal direction. So this is the horizontal direction. My components of momentum in the horizontal direction, they are also going to be equal to 0. My momentum components in the vertical direction, they would also be equal to 0 because overall the final momentum is coming out to be 0. So let's look at the first horizontal component of one of the particles. So this particle over here, like this in orange, this particle over here is traveling at 6 meters per second in this direction. So its horizontal component is going to be this one. I'm going to mark that horizontal component. We're going to make a triangle, and this would be my horizontal component. This line over here would complete that triangle. This component is the horizontal component for this particular particle. The velocity is 6 meters per second in this direction. So the angle that it's making with the horizontal is theta. So the velocity component would be 6 meters per second into cosine of theta. So my velocity vector in the horizontal direction for this particle would be 6 cos theta. So the particle's horizontal component, mass into velocity, it's 2m. So it's 2m mass into velocity, mass is 2m, multiplied by the horizontal velocity component, so it's going to be 6. cosine of theta, and this would be my momentum, my horizontal momentum, and I'm going to call this particle 1. So let's call this particle 1. This is the horizontal component for particle 1. And I'm also going to add a negative sign in front of it. The negative sign is going to be there because I'm taking this direction, this horizontal direction, as the positive direction. To the right is positive. So if it's moving to the left, that would be the negative direction of the horizontal component. So it's going to be negative 2m6 cosine of theta. The velocity, horizontal velocity, would also be minus 6 cos theta. So I'm taking this direction as my negative direction. And let's move in a similar way, move to this other particle over here. This particle is going to be called, I'm going to call this particle 2. Its horizontal component would be in this direction. So I'm going to draw a triangle, a vector triangle. This over here is the horizontal vector velocity, which over here is 8 meters per second, but it's at an angle of theta with the horizontal. It's 8 meters per second. So the velocity component, the horizontal velocity component, is going to be 8 into cosine of theta. So I'm going to write it over here. My horizontal component is coming out to be 8 cosine of theta, and I'm going to take that as positive because this direction I'm taking as positive. So the momentum for particle 2, the horizontal component of this momentum, is going to be mass, which is 1.5 m multiplied by 8 cosine of theta, which is the horizontal component of velocity. So this particle is going to have a horizontal momentum component, which is going to be this over here. And finally, the third particle over here, this is particle number 3. Particle 3, this is making an angle of 90 degrees with the horizontal. If it's at 90 degrees, that would mean that it is not going to have a horizontal component. This particle is not moving in either this direction or this direction, but it's moving in the vertical direction. So it's only going to have a vertical component. There is no horizontal component. So I can safely say that the momentum in the horizontal direction for this particle 3, it's going to be equal to 0. Now finally, using the principle of conservation of momentum, the initial momentum is 0, so the final momentum must be 0 as well, which means that its horizontal components and its vertical components must be equal to 0. So I'm going to sum up horizontal components of momentum, and I'm going to make them equal to 0 because my final momentum is 0. So let's start with particle 1. The momentum is minus 2m into 6 cosine of theta. Then this other component, particle 2, has a horizontal component of 1.5 m into 8 cosine of theta. And the third particle had a horizontal momentum of 0, so that's 0. And the sum should be equal to 0. Now, if I look at this equation, the sum of the horizontal components of my momentum, I'm running into a trouble because I cannot make, using this equation alone, I can't really figure out what the value of theta is going to be. I cannot make it the subject of the equation and find the value of theta. What I'm going to do is I'm going to start calculating the vertical component of momentum as well, and the component would be in the vertical direction. So the vertical component of this particle P1, the one that I'm shading in pink, in this direction, it's going to be P1, which has a mass of 2m. So mass into the velocity, the vertical component of velocity. The angle is theta with the horizontal, it's 6 meters per second. So the vertical component is going to be 6 sine theta. So this is for particle 1, the momentum for particle 1 in the vertical direction. Similarly, if I try to calculate the vertical component of particle 2, shading over here, its velocity is 8 meters per second, and it's at an angle of theta. So the vertical component in this direction would be 8 sine of theta. So it's going to be, for particle 2, the vertical component, they're both downwards. So the vertical component is going to be, 1.5 m mass into 8 sine of theta. And I'm going to take this downward direction as the negative direction, so I'm going to put a negative sign with them. So because both these particles are moving downwards, the vertical component would be in the downward direction. Then you have this particle 3. This is in the upward direction. It's not making it at any angle with the horizontal, so it's simply going in the vertical direction. So it's vertical component for particle 3, this particle over here. For particle 3, the vertical component of momentum is going to be, 3 multiplied by 3m is the mass. So it's going to be, and I forgot to put an m over here as well. 3m is the mass, and it's going at 7 meters per second. So that's the vertical component in the vertical direction. So again, what I'm going to do is I'm going to now sum up the vertical components instead of the horizontal components, because I've not been able to figure out a way to figure out the value of theta if I sum up the horizontal components. So vertical components would be, it's going to be particle 3, the momentum of particle 3, plus the vertical momentum of particle 2, plus the vertical momentum of particle 1. The values for particle 3 are 3m into 7, and that is positive. For particle 2, it's minus 1.5 m into 8 sine theta, and for particle 1, it is minus 2m into 6 sine of theta, and these vertical components must also be equal to 0. So vertical component of this particle is 2m into 6 meters per second sine of theta. Over here it's 1.5m into 8 into sine of theta, and the vertical component of this is 3m multiplied by 7. Now if I look at this equation over here, this equation over here is solvable. I can make theta the subject of the equation, and I can figure out the answer. What I need to do is, the first thing that would happen is that the m would get cancelled out. I can divide the whole equation by m, and the m gets cancelled out, and I can take sine theta as a common factor, and it's going to be minus 1.5 and minus 2, and I can take 21 on the other side. This would be negative. I can take 21 on the other side. That would become minus 21, and we can get rid of this negative value. Actually, let me make a few corrections. I think I got that wrong. It's going to be it's minus 1.5 multiplied by 8. So if I get this entire term on the other side, if this entire thing on the other side, it's going to become positive. So it's 3 into 7, which is 21. It's being multiplied by, if I take sine theta common, then it's going to be minus 1.5 multiplied by 8 plus 2 multiplied by 6. And taking this entire thing to the other side, it's going to be 1.5 into 8 is probably going to be 12. Plus 2 into 6 is also going to be, it's also going to be 12. So it's 21 divided by 24. And then finally taking the inverse sign, so this would be sine minus 1, this entire thing, 21 divided by 24. My answer comes out to be equal to 61 degrees. If you do the calculation, it's going to be 61 degrees. Theta, the value of theta is going to be equal to 61 degrees. So going back to my original diagram, this theta over here is coming out to be equal to 61 degrees. So both these thetas, 61 degrees over here and 61 degrees over here as well. In this next part, part 2 of the question, you are supposed to calculate the ratio of the kinetic energy of fragment of mass 2m and the kinetic energy of the fragment of mass half m. So I just need to apply the formula for kinetic energy, which is half into mass into half mv square. So for this particle, I'm going to put in the values divided by the kinetic energy formula, half into m into v square. For this second particle, so let's go back to our diagram, the 2m particle. If you look at the 2m particle, we don't need to actually look at the diagram, it's written over here. 2m particle has a velocity of 6 meters per second. So going back, velocity is 6 meters per second. So it's going to be I'll actually cut out this half, it's going to get cancelled out. So it's mass, which is 2m into 6 meters per second squared. So this would be squared divided by the mass of the second particle, which is 1.5 m. I'm actually cancelling out the m's as well because they're going to get cancelled out. And let's find the velocity of the second particle, 1.5 m particle. If you look over here, the velocity is given as 8 meters per second. So it's going to be 8 meters per second squared. So that's 8.0 squared. And the ratio that I'm going to get is, it's coming out to be 0.75. So that is the ratio that I am getting. In the following question, a child on a sledge slides down a steep hill and then travels in a straight line up an ice-covered slope as illustrated in figure 3.1. So this is where the child and the sledge, they are sliding down this slope, and then there's an ice-covered slope, and the momentum carries the child and the sledge up this ice-covered slope. And the question states that at t is equal to 0, they pass point A. So the sledge passes point A with speed 18 meters per second. So the speed is also given, it's 18 meters per second. And then he comes to rest at point B. The child applies a brake to the sledge at point B. The brake does not keep the sledge stationary and it immediately slides back down the slope towards A. So at point B, what happens, it comes to rest at point B, and after coming to rest at point B, the brake does not keep the sledge stationary, so the sledge starts moving down the slope after it stops at point B. Now the variation with time t of the velocity v of the sledge from t is equal to 0 to t is equal to 24 seconds is shown in figure 3.2. It's move to figure 3.2, and this is what's happening. So at t is equal to 0, the speed gradually decreases, and this is the point, this is the rest point, this is the point B where the child is at rest. The speed, if you look at the speed at this point, at 12 seconds, this axis is time, so at 12 seconds, the velocity is 0. So this is what's happening. If you go back to the image again, so the sledge is traveling at 18 meters per second. So the initial point, this is 18 meters per second on the graph, and it's going to decelerate. It's going to slowly, gradually, the speed would decrease and it would reach point B. And after reaching point B, the sledge goes in the opposite direction. So the velocity would have a negative sign and the velocity would start to increase again. So this is exactly what's happening. After 12 seconds, it comes to rest. The sledge starts traveling backwards. The velocity is in the backward direction. And this is the slope. The velocity is now increasing, but in the negative direction, which means it's going in the opposite direction. So the first part of the question is, state the time taken for the sledge to travel from A to B. So initially at 18 meters per second, it's traveling. Slowly, gradually, it decreases in speed, reaches rest state. The velocity becomes equal to 0 at B. So this is point B. So how much time did it take? It took the sledge exactly, if you look at this, it took the sledge 12 seconds. So you can show this on the graph. Make sure to label it on the graph. This would be a good practice. Label this point as A and label this point as B. So it's going to take the sledge 12 seconds to reach point B. So that is the answer for this part. Now moving to the next part of the question. The next part of the question is determine the displacement of the sledge up the slope from point A at time t is equal to 24 seconds. Now to find displacement of the sledge up the slope from point A to time t is equal to 24 seconds, I'm going to go back to the graph. So if I go back to my graph, you'll notice that you're supposed to calculate displacement from this point, from A, and from A to t is equal to 24 seconds. So we have to reach this point. So we need to calculate the total displacement from point A at t is equal to 24 seconds. So this is the point that we need to calculate. What is the total displacement? Now the first thing is that this is a velocity time graph. Velocity into time is distance, and remember, a velocity time graph, the area under the graph is always distance. It's the distance covered. So I'm going to first try and find out the distance that is covered from point A to point B. So if you go back and see the slope, the first distance that I'm going to try and cover, it's going to be from point A at t is equal to 0 to point B. So what is the distance that is covered from point A to point B? So this is my first task. So going back to my graph, the distance covered, because at B the sledge comes to rest. So in the first 12 seconds, it would be area under the graph, which is going to be half into velocity, which over here is 18 meters per second. So this is 18 meters per second. So we're going to write the formula of the area of a triangle. The time that is taken is 12 seconds. So it's 12. And we can simplify this. It's going to be 2. This would become 6. So it's 18 into 6. And this comes out to be equal to 108 meters. So that comes out to be equal to 108 meters. Going back to my graph. So in the first 12 seconds, the distance that is covered from A to B is 108 meters. So this is the distance that is covered by the sled as it climbs to point B. And this takes 12 seconds. So in 12 seconds, it's covering 108 meters. But after covering after reaching point B, the sled starts to move in the opposite direction. So the velocity becomes negative. So now I'm moving to the next part. After taking rest at B, it now starts to move, the velocity starts to move in the opposite direction. So in the next 12 seconds, this is the velocity time graph area. This is the area that is covered, because now the sled is moving backwards. This sled over here, after reaching point B, it's going to start moving backwards. It's going to go down the hill back again. So we're going to calculate how much distance it travels. So again, it's going to be area in this triangular region. So it's going to be half into, we need to find what this negative velocity is as it is moving down the hill at 24 seconds. And this negative velocity at 24 seconds would be 6 meters per second. If you yes, it's going to be approximately 6 meters per second. So my area over here, this area over here, it's going to be half into the height, which is over here is 6 meters per second, into the length, which is time over here. This length over here is time. So that is 12 seconds. So it's basically 2 and 12 would cancel out, that 6. So it's going to be 36 meters. So going back to my diagram, so the issue now is that it took 108 meters to climb up. That's the total distance between A and B. And when it is moving back at t is equal to 24 seconds, the sledge has only covered 36 meters. So moving upwards, it covered 108 meters, then it started moving backwards, and up till time t is equal to 24 seconds, it had only covered 36 meters. So we need to find displacement. The net displacement in this case from point A is going to be, it's going to be this distance over here. So it's basically 108 meters, and from that 100 meters, I'm going to subtract 36 meters, so it's 108 108 meters minus 36 meters. So going back to my question now. So calculating displacement, it's so displacement is going to be 108 meters minus 36 meters, and the answer comes out to be, it comes out to be equal to 72 meters. So that's the displacement from point A at time t is equal to 24 seconds. Now in the next part of the question, let's move to point C now. You're supposed to, the question is, show that the acceleration of the sledge as it moves from B back towards A is 0.5 meters per second square. So we need to find, we need to prove that the acceleration down the slope is this value over here. So going back to my diagram and the two graphs. So moving backwards, we're starting at rest B. The initial velocity u is going to be 0. The final velocity, if we look at the graph which is below here, so the final velocity in the graph at t is equal to 24 seconds is 6 meters per second. So you're basically starting at this point over here, 0 meters per second, and you're moving now at 6 meters per second as you're going down the slope, and the time it takes is between these 2 points is 12 seconds. So in 12 seconds you're going from 0 to 6 meters per second. Now moving back to our question. So I've replicated the diagram over here. Initial velocity is 0 meters per second. Final velocity is 12 meters per second after 12 seconds. So 12 seconds traveling down the slope, the velocity becomes 12 meters per second. And I need to find acceleration. Now I'm going to use the simple formula, which is V equals U plus AT, or we can write it the other way around. Acceleration is the change in velocity, V minus U, divided by the time it takes for that change in velocity. So it's the final velocity is 12. The initial velocity is the final velocity is actually 6 meters per second. I've actually made a mistake over here. So it's 6 meters per second in the graph. So it's 6 meters per second minus the initial velocity, which was 0, and the time it took was 12. So according to this, my acceleration is coming out to be equal to 0.50 meters per second square. So this is my answer, and this is the value that I have proved. Now in the next part of the question, if you move to the next part of the question, you have the child and sledge have a total mass of 70 kg. The component of the total weight of the child and the sledge that acts down the slope is 80 newtons. So this is the component that's acting down the slope. And you're asked to determine the frictional force on the sledge as it moves from point B towards A. Now what this basically means is that you have, this is your slope. You draw the slope, this is my slope. This is where the sledge is. So let's think of this box as your sledge, and the weight downwards is 70 kg or 700 newtons approximately, or 70, let me write it as 70 G. G is the acceleration due to gravity, and you take it as 9.81. So this is the force that's acting downwards. The component of the total weight of the child and sledge that acts down the slope, this component over here that's acting downwards towards the slope, the component of the weight that's acting in this direction is 80 newtons. Now there's going to be a frictional force that would be acting in the opposite direction, trying to stop the sledge from moving. So there is a frictional force, and right now this frictional force is unknown. I don't know what that frictional force is, but that would result in the net resultant force. So it's basically 80 newtons downwards minus the frictional force Fr. So there's a force that is downwards. This downwards force is greater because the sledge is moving downwards, it's accelerating downwards. So that means that there's a net resultant force that's acting in the downward direction. So it's 80 newtons minus the frictional force that would result in the resultant force, or the net resultant force on the sledge. This net resultant force can be calculated because I know the mass of the sledge, which is given as it's given as 70. So 70 kg, that's 70 kg, and I know the acceleration down the slope. The acceleration down the slope, which was also given in the previous part, is 0.5 meters per second square. So F is equal to ma. So mass into acceleration down the slope is 0.5 meters per second square. So this would be my net resultant force that's acting downwards. The body is moving at 0.5 meters per second square, and the mass of the body is 70 kg. So we just need to solve this now. It's 80 minus the frictional force, and if I make the frictional force the subject of the equation, it's going to be 80 minus 70 into 0.5 would be equal to 35. So 70 multiplied by 0.5, half of 70 is definitely 35, and this would be equal to my frictional force, which would come out to be, if I subtract 35 from 80, that would give me 45 newtons. And that is the correct answer, 45 newtons. That's your frictional force. And then moving to the next part of the question. The next part of the question wants us to calculate the angle theta, the slope of the slope to the horizontal. Now again, I'm going to redraw this diagram quickly. So there is a sledge over here, and it has a downward weight the downward weight is 70 kg or 70 Gs. That's the downward weight. And the component of this force, this downward force, is 80 newtons. How do you find the component down this slope? The way you find the component is you make a triangle. So let's draw a triangle. And this component over here of the same force, this force can be divided into two components. One would be your vertical component, and the other one would be your horizontal component. So the component of the force, of this particular force down the slope, is going to be this force over here. And if I use and I don't know what that force is, so if I use this angle over here is theta. Now I can try to calculate this theta, because if I take sine of theta, or cos of theta, if I take cos of theta would be adjacent, which is this component of the force down the slope. That was 80 newtons. So this over here is 80 newtons. So this is adjacent over the hypotenuse down this. The original force or weight acting downwards was 70 G, or 70 into 9.81. And if I solve this, I'll be able to calculate the value of theta. Let's call it theta 1, because this is not the theta that we are actually trying to calculate. So my answer comes out to be, if I take the inverse of theta, the inverse of this entire thing, it's going to come. This value comes out to be equal to 83.3 degrees. So this angle is now known. It's 83.3 degrees. And we had to calculate the angle of the slope from the horizontal. So we were interested in this theta over here. So this would be our theta. Remember, in a triangle, all angles must add up to 180 degrees. This already is a right angle. So I'm going to add theta plus theta 1, which is this value over here. It's 83.3 degrees. And plus I'm going to add 90 degrees, and they should all add up to be equal to 180 degrees. So 90 gets cancelled out. This would be left with 90. Then I take 83 on the other side. So my value for theta, this theta over here, this would come out to be equal to 6.7 degrees. So that is the angle of the slope with the horizontal. This is the horizontal. So this is the angle of the slope with the horizontal. It's coming out to be equal to 6.7 degrees. The next part of the question is on the Doppler effect. The child on the sledge blows a whistle between t is equal to 4 and t is equal to 8 seconds. The whistle emits a sound of frequency 900 hertz. The speed of the sound in the air is also given as 340 meters per second. A man standing at point A hears the sound, and you're being asked to determine the initial frequency of the sound heard by the man. Now, to solve this question, I need two things. One is, what was the velocity at t is equal to 4 seconds, and what was the velocity at t is equal to 8 seconds? So I'm going to go back to my graph and see and check what the velocities were at t is equal to 4 seconds. Actually, I just need to find the velocity at t is equal to 4 seconds because I need to figure out the initial frequency of what happens. So this is my velocity time graph. T is equal to 4 seconds. This is 4 seconds over here. This is the point t is equal to 4 seconds. So on my graph, it's probably 12 meters per second. So if you look carefully, it's coming out to be equal to 12 meters per second. So that's the speed at which the sled is moving. And now we need to figure out where was it moving. I'm also going to note down the velocity at 8 meters per second. The velocity is now actually slower. So it's coming out to be over here. So this is around 6 meters per second. So the velocity decreases. It's 12 meters per second at this point. And at this point over here at 8 seconds, the velocity, if I make a line, the velocity at 8 meters per second is almost half, or exactly half, 6 meters per second. So these are my two velocities. I need to look at the diagram as well to figure out what was happening. So this is my diagram. If you look at this diagram, the person is standing at point A. So let's say there's somebody standing at point A and he's listening to the whistle. Now the sled, it moves slowly and eventually moves to this point at t is equal to 4 seconds. Whatever that point is, let's say it's approximately over here. And then the sled moves to t is equal to 8 seconds. If you go back to the diagram, you'll notice that at t is equal to 12 seconds, the sledge has come to rest because it's going up the hill. So the sledge is slowly decelerating. So at t is equal to 4 seconds, there is whistling going on. So this is the point where whistling is done. So the sledge is whistling. And the waves from the whistle, they would eventually reach point A. And that's where the whistle would be heard. So I've made a simplified diagram over here. This is the sledge moving away from point A. And at t is equal to 4 seconds, the sledge is traveling at 12 meters per second. It's traveling up the hill. So it's slowing down. Eventually, it's going to slow down. So this is what's happening. The sledge or the child on the sledge is blowing a whistle. And this is what Doppler effect is. That the sound, frequency of the sound behind it is going to be lesser because the sound waves or the sound fronts, they're going to get spread out because the sledge is moving in this particular direction. It's moving in this particular direction. And wave fronts in front of the sledge, they're going to be closer together because the sledge is moving in this direction. So the sound that is produced, the other sound waves would also be produced and they would all compress together because the sledge is moving in this direction. So the frequency of the sound would be lesser in front of the sledge and the frequency of the sound would be greater behind the sledge. It's going to be lesser behind the sledge and greater in front of the sledge. Now the formula for calculating the change in frequency of the sound waves, the frequency over here decreases, the frequency of the waves over here decreases as the person is moving. That formula is this given over here, where v is the velocity of the sound in air. That's 340 meters per second. So it's going to be 340 over here, and it's going to be 340 over here as well. The velocity of the observer is going to be 0. The observer is simply standing over here. There's a stationary observer. So there is no velocity. This velocity, v observer, is going to be 0. And the velocity of the source or the person that's producing the whistle he's traveling at 12 meters per second. So that is 12 meters per second. So it's going to be, that is 12 meters per second. So it's going to be minus 12. And the other thing is, the original frequency of the sound is given as 900 hertz. So this over here is 900 hertz. So we're going to calculate our new frequency, which is going to be, it's going to be 340 divided by 340 divided by 340 plus 12. I'm going to take it as plus 12. This Vs is because the source is moving away, which means I'm not going to take it as 12 meters per second, but as minus 12 meters per second. Remember this, if it's moving away, this would be taken as plus 12 meters per second. So this would become 340 plus 12, and I'm going to multiply it by 900 hertz, and the value that I'm going to get is going to be, it's going to be 870 hertz. So this would be my answer to this question. So remember this formula, be careful with this formula, V plus V observer and V minus V source. But if the source is moving away from the observer, then this should become, the signs should change. Because if it's moving away, instead of 12 meters per second, this would be taken as minus 12 meters per second. Because this direction towards the detector is taken as the positive direction. So this would be taken as the negative direction because it's moving away from the source. So the sign of this V source is going to change, and it would become 340 plus 12, and so using the formula I'm getting 870 hertz. Now the next part of the question is that we need to describe and explain qualitatively only the variation, if any, on the frequency of the sound heard by the man. So what happens to what they're basically asking is that if the observer is standing over here, so initially we calculated that the frequency is decreasing, it's 870 hertz at t0 4 seconds. But this sledge, remember it's moving up the hill, it's slowing down, it slows down and it comes to rest. If the sledge comes to rest, which means that the Doppler effect is going to be lesser and lesser because the source of the vessel is not going to be moving that fast. So initially it was moving very fast at 12 meters per second. Remember, we also figured out that at t is equal to 8 from the graph which we previously saw, the sledge was moving at 6 meters per second. So which means that the speed is decreasing. So, and it's eventually going to come to rest at t is equal to 12 seconds over here. So the sledge is slowing down. The Doppler effect would be lesser and lesser. Eventually the frequency of the sound would come back to the original frequency. So initially if it's moving very fast, you're hearing a low frequency. You're hearing 870 hertz over here. The observer is hearing 870 hertz. But if the speed of the sledge is becoming lesser and lesser, the frequency of the sound would eventually become, if the sledge stops and it slows down and gradually it stops, the frequency would come back to 900 hertz and the Doppler effect would finish. So the answer to this question, qualitatively, what happens to the frequency of the sound, to write that the frequency of sound increases. And eventually the Doppler effect would be minimum and it would decrease as well. The frequency of sound increases because the sledge velocity decreases. So gradually the sledge velocity is going to decrease. In the following question, the first part of the question states that we need to define the wavelength of a progressive wave. What does the term wavelength mean? What's the definition of the term wavelength? So a wavelength is the minimum distance. So it's the minimum distance between two wavefronts. So it could be the minimum distance between two crests or two troughs. So here I've shown an example of a wave. This is my wave. So it's the minimum difference between two wavefronts. So this it could be the distance between two crests, or it could be a distance between two troughs. So that is lambda. It's known, the symbol is lambda, and this is what wavelength is. In the next part 2 of the question, state what is meant by an antinode of a stationary wave. So we need to define what an antinode is. So the first thing is, what is a Stasi wave? Stasi wave is when a wave is reflected by a partition. So there is a wave that is traveling. This wave, the dark blue line, it's traveling and it gets reflected back. So the wave and its reflected wave, they start interfering with each other. This would be your node. This point over here would be your node, the position where the wave is going to have minimum amplitude or no amplitude at all. And this point over here is going to be your antinode. This is the point where the wave would oscillate. This is another antinode. So the wave particles would be oscillating and would have maximum oscillation. So it's the point where there is maximum amplitude. So that is what is meant by an antinode of a stationary wave. The next part of the question reads that a loudspeaker producing sound of constant frequency is placed near the open end of a pipe as shown in figure 4.1. So this is your loudspeaker over here. There's a piston that's movable, and I think the piston is moving at a speed of 0.75 centimeters per second in this direction. And the distance is x. The loudspeaker and the piston, the distance between them is x. So what is the question asking us to do? The question, a movable piston is at a distance x from open end of the pipe. Distance x is increased from x is equal to 0 by moving the piston to the left with a constant speed of 0.75 centimeters per second. The speed of the sound in the pipe is 340 meters per second. A much louder sound is first heard when x is equal to 4.5 centimeters. So when x equals 4.5 centimeters, a loud sound is heard, which basically means you're hearing an antinode, because a Stasi wave is going to be produced. So this is how the sound wave would look like. A node would be produced at this particular point. This would be your node that would be produced at the piston. The wave is going to come in and it's going to get reflected. This would be the point where the amplitude of the wave would be maximum. The particles would be vibrating very loudly, and this is the point where a node would be formed, where the wave and its reflected wave, they're going to superimpose and they are going to get cancelled out. So the particles are not going to be vibrating at the node. So the antinode, a loud sound, would only be produced if an antinode is present at the loudspeaker. Now the question goes on to state that we need to determine the frequency of the sound in the pipe. The frequency of the sound is, you must have noticed that if I extrapolate this wave, this is the first crest. So if I continue this wave, this would be your trough. So this point over here, this distance x is equal to 4.5. If you look at this distance over here, this distance is lambda by 4. This is lambda by 4. X is equal to lambda divided by 4. So it's quarter of the wavelength. You can see that the wave starts over here and ends over here. So this is your complete wavelength. We are talking about only this section. For an antinode to form the wave, this would be the crest, and this would be the node of that particular wave, that particular stationary wave. So lambda, the entire wavelength divided by 4, that is this point is lambda by 4, and we know that it is equal to 4.5 centimeters. So what we are going to do is we're going to apply the formula V is equal to, I'm going to apply the formula V is equal to lambda F. Now the question is about determining the frequency. We already know the speed of the sound, velocity of the sound is 340 meters per second. Lambda on the other hand is coming out to be equal to, lambda by 4 is coming out to be equal to 4.5 centimeters. So if I get rid of 4 from here, I multiply 4 over there, the wavelength is 4.5 multiplied by 4, which is 18 centimeters. and that 18 centimeters should be converted into meters. So I'm going to divide that by 100 into frequency. And the answer that I'm going to get for this is, if I solve this, the answer that I'm going to get is going to be 1900. It's going to be 1900 hertz. So if I solve for f, make f the subject of the equation, f would be 340 divided by, so it's going to be 340 divided by 0.18. And the answer is going to be 1900 hertz. So we've solved the first part. The question then goes on to state that after a time interval, a second much louder sound is heard. Calculate the time interval between the first louder sound and the second louder sound being heard. So we're now looking for the second louder sound. Remember, the piston is moving backwards. This piston is moving backwards. So as you move the piston backwards, the sound would travel a much larger distance. So if an antinode, a louder sound, is produced at this point, the wave, let's complete another, the wave is going to bounce back at this point. And this would be the point where, and this is how the second louder sound is going to be produced. So the piston must be at this point. It must be at this point. So that the wave travels one more cycle, gets reflected, makes a node at that particular point where the piston is. So the piston has moved to this point and gets reflected back, makes a node again, and then goes on to form an antinode. So when the piston slowly moves backwards, this is the point where the second louder sound is going to be produced. A stationary wave would be set up again, and the loudspeaker would, you'll experience a louder sound at the loudspeaker. So to produce a second louder sound, this is the extra distance the wave must continue or must travel. And we know that this distance, so the first loud sound was produced when the piston had traveled a distance of 4.5. Remember, lambda by 4, or quarter of the wavelength, we've already calculated, that's 4.5 centimeters. So the other loud sound would be produced when the piston would have moved this distance. And if you calculate this wave, it's 2 lambda by 4s. This is quarter wavelength. This is another quarter wavelength. This is another quarter wavelength. This would be equal to 9 centimeters. This part would be equal to 9 centimeters. This distance over here from the first position of the piston to the second position of the piston. This distance would be 9 centimeters. It's basically lambda by 4 plus lambda by 4. So what I'm going to calculate now is I'm going to figure out when would the sound be produced when the piston had moved 4.5 centimeters, and at what time interval would the sound be produced when the piston had moved 9 centimeters. Now moving back to my question, I just need to calculate the time it's going to take for the second loud sound to be produced. 9 centimeter would be the distance. And this piston over here is traveling at its, if you look at the speed of the piston, it's moving at 0.75 meters, centimeters per second. So let's just try and confirm whether it's moving at 0.75 meters. Yes, it's given over here, it's traveling at 0.75 centimeters per second. So we need to just use the formula of distance of speed. Speed was equal to distance divided by time, and I need to calculate the time because this is the point where the first loud sound was produced. This is the point where the second loud sound would be produced. We already know the speed, it's 0.75 but centimeters per second, so I'm going to take distance in centimeters as well. That's it's going to be 9 centimeters divided by time, and we just need to calculate, make time the subject of the equation. And if we do our calculations correctly, the answer is going to come out to be equal to 12 seconds. The following question reads that there is a solid cylinder is lifted out of oil by a wire attached to a motor and shows 2 different positions of X and Y of the cylinder during the lifting process. So this is a cylinder that was dipped in oil, And remember, oil is going to create an upthrust. I mean, there's going to be the weight of the cylinder that is going to be acting downwards. And this weight of the cylinder, this weight is pointing downwards. This would be counteracted by the force. Remember, the motor is pulling this this object upwards. So there's going to be tension in the wire, and there's going to be a force that would be applied that would be in the upward direction. Plus, there's going to be an additional force that would be the upthrust of the oil. The oil would also be pushing this piece of cylinder upwards. So if I balance these forces, weight would be pointing downwards, the tension in the wire would be pulling it upwards, plus the upthrust of the oil is going to be pulling it upwards. So let's call that U. So it's going to be W would be equal to F plus U plus upthrust of the oil. Whereas if you look at the second diagram, you'll notice that the cylinder is no longer dipped in oil, which means that the upthrust that the oil was exerting or pushing this cylinder upwards, there's not going to be any upthrust. So the upthrust would be missing over here. There's only going to be the weight of the cylinder that would be pointing downwards, plus the force or the tension in the wire that would be pulling it upwards. So over here, the force of the pulley upwards would be equal to the weight of the cylinder. The condition is that the forces must be in equilibrium, which means that there must be the cylinder must be moving. There should be no overall acceleration. If there is overall acceleration, that means there's going to be a net resultant force. So over here, the velocity is given as constant, and over here, I think the velocity is also given as constant. Is given as a constant. Let's read the question further and figure that out. If you read the next part of the question, the motor is fixed to an overhead beam. The cylinder has cross-sectional area of 0.18 meters per second square. Length is 1.2 meters and weight is 560 newtons. So a lot of information is provided in this part. The weight is given as 560 newtons. So we know the downward force that's acting. The length of the cylinder is given and the cross-sectional area of the cylinder is given. So we can figure out the volume of this cylinder using these two values, because volume is cross-sectional area into length. So if you multiply the two, you will find volume. And the density of the oil is also given. It's given as 940 kg per meter cube. Now, based on these two informations, we can figure out what volume of oil must have been displaced. What volume of oil would be displaced? Anyways, reading further, throughout the lifting process, cylinder moves vertically upwards with a constant velocity, which means that all the forces are balanced out. There's no net acceleration. It's a constant velocity, which means there's not going to be a resultant force. The viscous force of the oil acting on the cylinder is negligible, which means there is no drag force. This cylinder is slowly moving out of the oil. So we are assuming that one force is absent, which is the viscous force. The viscous force is, if you move an object out of a liquid, the liquid is going to drag it downwards. So if you move this object upwards, there's going to be a drag force. So the question states that there is no drag force. Now the first part is we need to calculate the density of the cylinder. Density is, the formula for density is mass over volume. So we're going to use that formula. We can figure out the mass of the block of cylinder. If you look at the mass of the block of cylinder, remember, for this cylinder we were given the weight, and weight is W is equal to mg. So you're provided the weight, and weight is W is equal to mg. So using this formula, we know that the weight is 560 newtons. Mass would be into 9.81. So if I rewrite the formula, I can substitute the value of mass from this, and it's going to become my density. My density is going to become, the mass would be 560 divided by 9.81. And I need to divide it by the volume. And the volume, we already figured this out. The cross-sectional area of the cylinder was given and the length of the cylinder was also given. So we need to multiply the two. It's going to be 0.018 multiplied by 1.2 meters. So if we do that and if we calculate this, this is the value of mass that we got from this W is equal to mg equation. The length area and cross-sectional area gave me volume, so density is equal to mass over volume. And my answer for this is going to come out to be equal to 2600 kilogram per meter cube. In the next part of the question, you're being asked for the cylinder at position X. So the cylinder at position X, show that the upthrust due to the oil is 200 newtons. We need to find the upthrust due to oil. So going back to my diagram, if you look at the diagram, and this is the cylinder that's at position X. So if you look at the diagram, the first thing we need to know is how much oil is displaced, because the upthrust is caused by the displaced oil. So we need to figure out the amount of displaced oil. Now the amount of displaced oil would be equal to the volume of the cylinder. So the volume of the cylinder is already known. It's cross-sectional area into length. So that is given. So we would be able to figure out how much oil has been displaced. So the volume is going to be 0.018 multiplied by the length, which is given as 1.2 meters. And this volume comes out to be equal to 0.0216 meters. So this is the amount of oil that has been displaced. So I've copied my working over here. So the volume of oil displaced is 0.0216 meters. The other thing that's given is the density of the oil. So over here, the density of the oil is given. Remember, density is mass over volume. Using this formula, we know the density of oil, which is given as 940 kilogram per meter cube. So that's provided. So I'm going to take that 940 kilogram per meter cube, and I'm able to figure out the mass because the volume is also known. It's this should be in meter cubed. It's 0.0216 meter cubed. So using my formula for density is equal to mass over volume, I can figure out the mass of oil that has been displaced. So mass of oil that has been displaced is 940 into 0.0216, and the value comes out to be 20.304 kgs. So this is the amount of or the mass of oil that has been displaced by the cylinder that's been dipped into it. Now upthrust is equal to the weight of oil that has been displaced. We know the mass of oil, which is coming out to be equal to 20.304 kg. So the weight would be m into g, which is the mass is 20.304. I'm going to multiply it by gravitational force, which is 9.81 meters per second square. So my answer would come out to be approximately equal to 200 newtons. So this would be my upthrust, and this is how I've proved it's equal to 200 newtons. So this is the solution for this part of the question. In the next part, we are being asked to calculate for the moving cylinder at position X the tension in the wire. So if you go back to our diagram, you would have noticed my working earlier as well. This is the tension force that is being applied by the wire upwards. It's in the upwards direction, weight is downwards, and then there is upthrust. So I wrote down an equation that weight of the cylinder is equal to force, which is the tension in the wire, plus the upthrust. So these two forces are in the upward direction, the weight is in the downward direction. So using this this relationship, I'm going to figure out the force or the tension in the wire. I know that the weight is 560 newtons. I know that the upthrust is 200 newtons. So this is what's happening. W weight, which is 560 newtons, should be equal to the upthrust, which we calculated in the previous part, is 200 newtons, plus the tension T in the wire. So this is the rough diagram that I've sketched. Weight is pointing downwards, wire tension is pointing upwards, and the upthrust, the liquid oil, is also pushing this object upwards. And solving for T now, tension T would come out to be equal to, it's going to come out to be equal to 560 was the weight, 560 minus 200, which would be equal to 360 newtons. In the last part, part 2, the power output of the motor is to be calculated. We know that the object is moving upwards at 20 meters per second. So we know the velocity with which the motor is pulling the object upwards. Let's go back to the diagram and recheck. Yes, over here, it's if you look at the diagram, the motor is pulling the object at 0.020 meters per second. The force or the tension in the wire, we already calculated that, came out to be 360 newtons. So we know the force and we know the velocity as well. So let me first correct this. It's 0.02 meters per second. So power, the formula for power is force multiplied by velocity. The force is 360 newtons. And the velocity with which the motor is pulling the object upwards is 0.020 meters per second. And this value comes out to be equal to 7. If you calculate this, it's going to come out to be equal to 7.2 watts. Moving to the next part of the question. The question now is that the cylinder is raised with constant velocity from position X to position Y. State and explain the variation, if any, of the power output of the motor. As the cylinder is raised, numerical values are not required. So what happens as the cylinder is pulled out of the oil? Remember that there was tension T in the wire. There's tension T in the wire. There's W, the weight of the object, and then there is the upthrust caused by the displaced oil. So as the cylinder moves out of the oil, less oil would be displaced. So less oil is displaced. And if less oil is displaced, that would mean that the upthrust is going to decrease. It's going to be lesser. So since the weight is equal to the upthrust plus the tension T in the wire, the motor is pulling it upwards. So upthrust and tension T, those are the forces in the upward direction. The W weight is in the downward direction. So weight is equal to upthrust plus tension T. Now upthrust decreases as the cylinder moves out of the oil. Less oil is displaced, so upthrust is decreasing, which means that for the motor to pull up this weight, the tension T must increase. So this should be increased. It would become more difficult for the motor to actually pull this cylinder upwards because the upthrust value is going to be lesser. So more tension, more force needs to be applied by the motor. So if more force needs to be applied by the motor, so what would it do to the power output? Remember, power was force into velocity. So if you want to keep the velocity constant, the force is constantly increasing. So the power would increase as well. The power output of the motor, more power from the motor must be used. So power output would it's also going to increase. So you're going to answer this question in 3 points. The first point would be that the upthrust, less oil is displaced. So the upthrust is decreasing, which means that more force, you can use this relationship and you can then talk about more force needs to be applied by the motor. And if more force is applied, then the power output, because power is force into velocity, the power output of the motor is going to increase. Now in the next part of the question states that the rate of energy output of the motor is less than the rate of increase of gravitational potential energy of the cylinder. Now remember, this is weight. This is the gravitational potential energy. This is you're doing work and you're increasing gravitational potential energy as you lift this solid upwards. So weight, you're doing work against this W. But remember, work is being done by the motor, but it's also being done by the upthrust. Some work, because lifting the object, the upthrust is also contributing. It's also lifting the object. So some work is being done by the upthrust. So the motor over here is pulling the object, but the upthrust is also adding some work to it. So the motor has to do lesser work. Less work would be required from the motor, which is why the increase of gravitational potential energy of the cylinder is greater, whereas the rate of energy output of the motor is lesser. So less work would be done by the motor. Question. The first part of the question states you have to define what Kirchoff's first law is. So the law is defined as the sum of currents into a junction equals the sum of currents out of a junction. Now this basically means that if there is a node where all three random wires are connecting to that particular node, and there is current flowing into the node and there are two currents that are flowing out of the node, then the sum of currents going into this junction, which is I1, should be equal to the sum of currents that are coming out of the junction, which means that I1 would be equal to, it's going to be equal to I2 plus I3. It's going to be equal to the sum of currents that are coming out of the junction. The question states that Kirchoff's first law is linked to the conservation of a certain quantity. State this quantity. So it is related to the conservation of the certain quantity. Is when you talk about this certain quantity, it basically means charge. It's charge that needs to be conserved. So the amount of charge that's flowing into a node and the amount of charge that's leaving out of the node, that should be equal. So current going in and current coming out, they must be equal. Current is the rate of flow of charge or the amount of charge that flows per second. So it's the conservation of charge that we are talking about when we talk about Kirchoff's first law. In the next part of the question, a battery of electromotive force EMF 8 volts, so that's 8 volts. And internal resistance is 2 ohm is connected to a resistor X and a wire Y as shown in figure 6.1. So there is a resistor, 15 ohm resistor is placed over here, and in parallel there is a wire X which has resistance RY. And the current is shown, it's the current that's going through this wire is 2.5 amperes. Now moving to the next part of the question, the next part of the question states, the resistance of X is 15 ohms, the resistance of Y is RY, the current in the battery is 2.5 amperes. You're asked to calculate the thermal energy dissipated in the battery in a time of 5 minutes. Now he's talking about inside the battery, there is this resistance 2. We know that power, if I try to solve this, the thermal energy that is dissipated, remember that thermal energy is work done. Work done is power into time. So power into time, the formula of power is I square R. Multiply that by time, which over here is 5 minutes, which is 5 into 60 seconds. So we need to calculate power into time. The current is 2.5 amperes, so that's we're going to use that current. So the current is 2.5 amperes, it's I square R, or 2.5 squared multiplied by the internal resistance of the battery, which is 2 ohms, multiplied by the time it takes, 5 into 60 seconds. So this would be the total energy that is dissipated in 5 minutes. And this value comes out to be equal to 3800 joules. So you can do this calculation on your calculator. The answer comes out to be equal to 3800. Over here 8 volts, battery is providing 8 volts, and what we can do is, there is this internal resistance over here, there would be some voltage drop, some energy that would be dissipated by this 2 ohm resistor. So we know that the current that is passing through this battery, this current is going through this 2 ohm resistor. So V is equal to IR. So the voltage of this resistor, internal resistance, is going to be the V is equal to IR, which means that it's going to be current 2.5 multiplied by the resistance, which is 2 ohms, so it's going to be 5 volts. So that means if the EMF or the voltage that is provided by the battery is 8 volts and there's a 5 volt drop on this resistance, so the net resulting voltage that would appear on the terminals of this battery, so let's assume that these are the terminals of the battery. So EMF is 8 volts and the voltage drop on the internal resistance so the voltage on the internal resistance is 5 volts. So your net output voltage is going to be, if you solve this, it's going to come out to be equal to 3 volts. So this is the voltage that the external circuit is going to see. On the terminals, it's going to be 3 volts. So let's answer that, the terminal potential difference. So it's going to be 8 minus 3 volts, which comes out to be equal to 8 minus 5 volts actually. And this comes out to be equal to 3 volts. Now, so this resistance Ry needs to be determined, and let's go back to our diagram first. Now, one thing that we have figured out so far is that the terminal voltage is 3 volts, which means that since these two resistances, they are in parallel, which means in parallel the voltages are the same. So 3 volts resistance would be on this resistance and 3 volts resistance would also appear on this resistance. What I can do over here is, if I look over here, what I can do is, I know the resistance and I know the voltage. So I can figure out the current in this resistor. So current I is going to come out to be equal to, it's going to be, since V is equal to IR, I would be equal to V, which is 3 volts, divided by R, which is 15 ohms. And the current comes out to be equal to 0.2 amperes, which now means that this wire over here, this particular parallel circuit over here is providing a 0.2 ampere current is going through it. And I can now figure out the current that is passing through this wire over here. The way I can do that is that I can apply Kirchoff's law, that since the total current that's coming out is 2.5 amperes, which means 2.5 amperes current is going to be the sum of this 0.2 ampere current and this current, let's call this current X. So 2.5 ampere current is equal to 0.2 ampere current plus the current X, which is going through this resistor Ry. Solving this, I'm going to get X as equal to 2.3 amperes, which means that 2.3 amperes current is passing through this wire whose resistance is Ry. Now finally I have the current that's passing through this wire and I have the voltage of this wire as well. So again I'm going to apply V is equal to IR. The voltage is 3 volts and the current is now 2.3 amperes. So V is equal to I into R. The resistance is Ry. So for this Ry, I can apply V is equal to IR. And I'm going to get my answer, which is making Ry the subject of the equation. And solving, it's going to be 3 divided by 2.3 amperes. And my answer is going to come out to be equal to 1 point. My answer is coming out to be equal to 1.3 ohms. So the resistance Ry would be equal to 1.3 ohms. So what I can do now is I can paste this working over here. I can take this working from this point and I can paste it as a solution in my answer. So here I have pasted the solution and the answer comes out to be equal to 1.3 ohms. Now moving to the next part of the question. The next part of the question states that you have a new wire Z has the same length but less resistance than Y. State two possible differences between wire Z and wire Y that would separately cause wire Z to have less resistance than wire Y. Now for a wire, the relationship that determines the resistance of a wire is first the resistivity. So what you can do is, This term over here is called resistivity. So the first difference you can have is you can have a different material, make the wire of a different material. So you can use a different material with a different resistivity. So each material has a different resistance. It offers a different resistance. So the resistance of a particular wire depends on the resistivity of that material, plus it's directly proportional to the length and inversely proportional to the cross-sectional area. So the bigger the cross-sectional area, which means the thicker the wire, the resistance would decrease. So state 2 possible. Now the problem is you're using the same length, so length would not be a factor. So it's either resistivity or you change the cross-sectional area. So the second difference would be the cross-sectional area. And you can also mention that resistance is proportional to 1 over A. In the next part of the question, you have part 2. You're given wire Y is now replaced in the circuit by wire Z. By considering the current in the battery, state and explain the effect of changing the wires on the total power produced by the battery. Now I've gone back to the circuit, and the wire Y is now replaced by another wire which is called Z. So what I'm going to do is, and remember Z had a smaller resistance, so let's make this a smaller resistance. Let's see what happens, because we don't need to do any calculations specifically. Let's make this a 1 ohm resistance. So I've decreased the resistance. Now if I decrease the resistance of this wire, the currents in the entire circuit, they are going to decrease. Remember, these two resistances are in parallel. So previously the resistances that were in parallel, there was a 15 ohm resistance. So I'm going to use the relationship with the total net resistance in a circuit that's in parallel. These two resistances are in parallel. So 1 over R is equal to 1 over R1, which is this resistor over here, plus 1 over R2. Previously the resistance was 1.3 ohms. So this is the total resistance that's being offered. If you try to solve this, it's going to come out to be equal to, this would be equal to 1.3 plus 15 divided by 15 into 1.3. And if you make R the subject of the equation, then this would become minus 1. So let's try and solve this first. And the answer that I'm getting is 0.836 ohms. Now what I'm going to do is, what I've done is actually I'm going to decrease the resistance. So let's assume that it was 1.3 ohms initially, now it's 1 ohm. So what would happen if I change the resistance of one of the resistors? Now it's 1 ohm, so this has been replaced by 1 ohm. So this entire formula would become 1 plus 15 into 1, which would be 15 over 15, which would be 1 ohm. So my resistance, total resistance, would actually increase. If I decrease the resistance of wire Y, the total resistance that the circuit is seeing is going to decrease. It's going to increase. Initially it was 0.836 ohms, now it's 1 ohm. So I just changed 1.3 ohms to 1 ohms just to see what would happen. So if the total external resistance is going to increase, it's becoming 1 ohm. Now resistance is proportional to current. V is equal to Y, resistance is proportional to current, assuming that you keep the voltage the same. So since resistance is proportional to current, if resistance increases, then the current would also increase, and the power output, power depends on, power is basically current into voltage. So since you have the same voltage, the EMF is the same, so power would increase as well. So going back to our question, what's happening? External resistance. So the net external resistance of the parallel, net external resistance would increase. And if that would increase, current is proportional to resistance. since voltage is constant, EMF is constant, current is proportional to resistance. So I would increase, and since power is current into voltage, voltage is the same, current is increasing, so P increases, or the output of the power output would increase. In the following question, the stationary nucleus X decays to form nucleus Y as shown by the equation. So there is decay going on, and the question states that in the above equation, draw a circle around all symbols that represent a lepton.